No? All of that is okay for you? So there will be several numbers. I hope you can try to memorize. Specific yield, commonly there's range from 0.1 to 0.3. That could be, sometimes could be smaller. And it related to the porosity because I mentioned that specific yield is for the unconfined aquifer system. And in the unconfined aquifer system, when we're talking about the storage concept, is the water released from the pore spaces. So the pore spaces is larger, so that means you can release more waters commonly. Yeah, clay is another issue. But for normal porosities, it can release the water. Is the maxima could be related to your porosity quantities. So the quantity could be around 10% to 30%. And for the specific storage or for the storativity in a confined system, they'll be relatively small, 10 to minus 3 to 10 to minus 5. So that means when you see a storativity values in the report or from reference, you will be able to understand is that from confined or unconfined. Okay, this is unconfined, this is confined. You can quickly understand what the values means. Okay, as I mentioned, if you are groundwater hydrologist, when you see hydraulic conductivity, you should have some images what's the material layer. And when you see the storage coefficients, you will also have the images. What's the concept for that? That's very important general concept for the experts in this field. Specific yield is the water released from a water-sparing material by gravity drainage. So commonly, if you take the core samples around, the water can gradually release if they are fully saturated, and we can estimate how much the water release. The specific yield is expressed as the ratio of the volume of the water yield from soil or rock by gravity drainage after being saturated, because we consider the fully saturated condition, so how much water released. So from saturations to the gradually drainage. And to the total volume of the soil or the rock. So that means if we have the total volume of the rock matrix or the soil matrix, and the SY value is how much water we can drainage. So VD is the volume of the waters that are drained from the total volume of the VT. So we're using the ratios, and then we can know how large is specific yield. So this definition is from the volumes, the pore volumes. And why we need to express this, because we propose another concept or another term called a specific retention. The term specific retentions describe the waters that is retained as a film on the surface of the grain or held in a small opening by molecular attractions. Okay, the specific retention is expressed as a ratio of the volume of waters that is retained after being saturated to the total volume of the soil or rock. So in the previous, we're using the VD. VD means the water we can drainage, and VR means the residual that we cannot drainage. Okay, so VR is the volume waters retained against the gravities. So it will be easy to imagine that VD is the water we can drainage out. VR is the residual. So VD plus VR will be the VV, right? VV is the total volume of the total volume of the void. Because we're considering the total fully saturated. If the pore space is full of the waters, we have the water amount is n, right? N values. If the unit is 1, so we have n values for the total waters. And the water amount can be drained out is VD. And VD divided by the total volumes will be the specific yield. And the residual part, VR, residual, is the water still in the pore spaces. They cannot be drained out naturally. Okay, so that's the VR. And VR divided by VT, the total volumes. We call this the retentions, specific retentions. Okay? So that means we can combine them together to have the equations. Later we will have show that. So the concept will be if there's a matrix like they have this kind of result, and there'll be, if there's granular, that means your water residual waters will be like the film across the volumes, so the quantity could be small. And if you have a pore spaces like this, you have the solid phases and you have the empty spaces, and some of the waters still be retained in the pore spaces. They cannot be drained out, or they are not easy to be drained out. Okay, so will be or this kind of system, fractured rock systems. In some place, if the pore space is larger, the water will be easy to release. But if the fracture is very, very small, they will have like the suction head, or they have the molecular attractions inside. So the water is difficult to be drained out. And commonly we use in the gravity drainage means they are natural drainage. We do not use in suction system to take the waters, or we do not drain out. We just let the natural drainage. So we will have some residuals here. And if we use in this kind of the figures, sometimes you will see these kind of figures. They illustrate like a saturation concept. Water content here, if we fully saturate, is the water content is 0.5. Although water content is another quantity, you don't need to memorize here. You just imagine that 0.5 is fully saturated, okay? And after you release the waters from the gravities, your water content will decrease, right? Your water content will decrease. And this one is the water, what's that? Not easy to imagine. That's the kind of the suction head. We can use in the suction head concept to describing, or using the head concept. But it seems the drainage behaviors is like they have the negative pressure. So commonly they will be negative. That means the pressures concept. So when your pressures become higher, that means you have higher suction head to take the water out. Okay, something like that. So that means for the whole processes, if your suction head or your suction pressure is very continuous increase, you can take the waters out. Initially, they are not easy to take out. So your decline, you can see that this pattern means your decrease is very slowly. They're moving very slowly. But in some of situations, like this pattern, this period, they moving very fast. But after approach you to this area, you increase a lot of the force to take out the water, but the water cannot be taken out. So we will have some residual, called residual water content here. That means even you increase your pressures to take the water out, they will be very, very difficult. So we have the residual part like this. And we call this part is the residual, the retention, specific retentions. And this one will be the specific yield. Because this part is you take the waters out, right? And this part is you cannot take waters out. Okay, so this curve, sometimes you will see this kind of this curve. I forgot exactly, maybe I forgot the term. Okay, yeah, you can check the reference book. So there's the water content continuous declines, but they will show we call it shape, S shape, or S shape. Okay, this is we call S shape. That means initially the moving is very slowly, and after that they're moving very quickly, and at the end they're moving much slowly. So the curve will like this. Okay, the drainage processes. Seems this one is for unsaturated system, so we are not very commonly see in groundwater hydrology. So the porosity defined previously is related to the specific yield and specific retentions. So we mentioned that if we combine specific yield and specific retentions together, they become the porosity, because the lower part is the total volumes, right? And the upper part will be water release, and the upper part will be water residual. And these two combined together is the porosity, or the pore space is VV. And VV divided by VT, so they become like this. So they have the relationship for the porosity and specific yield and specific retention. That is, the sum of the specific yield and specific retentions equal porosity. And the specific retentions increase with decrease of the grain size and also the pore space of the rock, soil or rock. So here is some values for your reference. We have the porosity for the soil, clay, sand. For example, we might see these several. So the porosity around these quantities. And specific yield means how much water we can release from the gravity. So you can see that commonly for the soil, you can get a large amount of the waters. And sand, we can get a large amount of waters. Gravel is also easy to drainage. But clay will be difficult to drainage. Okay? But specific retentions, since this is the, if we combine them together, it will be the porosity. So high specific yield, there will be less specific retentions. But clay will have a large amount of specific retentions. Because the pore space is very small, so the water is not easy to be released. So most of the water will be stored in the clay material, like that. So gravel, because they are very larger grain size, so the most of the water can be drained out. If your pore space is very small, they will easy to retain the waters or to sustain the waters inside. So the concept will be like that. Yeah, so there's some reference value for you. And for the storage concept, here is the one example for you to understand what the storage means. We know that the hydraulic conductivity controls the flow rate, right? The flow, if they are easy to flow or difficult to flow, you use the K value to control that. Your K value higher, you'll flow faster. Your K value smaller, you will flow slower. But what the storage means? What storage control the water levels, or what control the behavior for the groundwater variations. And S value commonly control the variation quantities. So right now we have these figures. We have this result is from the observation, real observation in Donggang River. So there will be several years. We can see that several year variations. There's a dry season, wet season, dry season, wet season. And we have two examples. One of that is Tuku here. I'm not sure exactly. Yeah, we have one is high variations. This one is for the Gaoshu, high variations. And this one is for the small variations. And which one is high S, which one is small s? Not exactly correct, but it is approximately, if all the background is the same, you can see the high variation and small variations, and you can have the concept. What the storage quantities you might have. Think about that for 10 seconds. Or maybe you need more, 30 seconds. Which one have high S value? Which one have small S value? Think about that. Which one have higher, larger S value? Do you make decision? Make decision. Vertical axis groundwater level. Groundwater level. So there's a groundwater level variation, observation. This is time and groundwater level. And for different wells, this is a lot of different well observations. So for example, this is Gaoshu station. They have the groundwater level observations from the wet season, dry season, wet season, dry season. So they have the variation. Okay, do you make decision? Which one have larger S values? This one? How many of you think this one have higher S value? 3, 4. Okay. How many of you think this one have high S value? 1. Okay. Let's take a look. This property is from the pumping test experiment. Okay. And we take a look. This to cool is this one, and 高速 is this one. To cool, we can take a look. This is SS value, SY values. So commonly, you need to check which one is the dominant, because sometimes they use in, we mentioned that the S value can equal to the SY and SS plus together. So to cool here, the T values is here, and 高速 the T value, you can take a look, they are quite similar. Commonly, the same order, we will say they are similar, T value or the K values. And S values here, this one, SY is larger, and SS is small. So that means to cool will represent the unconfined aquifer, because SS is small. So they combine together means there will be many unconfined aquifer. And this one, they could be similar. So they could be confined or unconfined. All of that could be similar. But you can take a look. That means to cool have higher SY values. 高速 have small SY values or SS values. Because we need to combine them together. So this one, when you combine, that means to cool have higher S, and 高速 have small s, right? So to cool have high S. 高速 have small s. So only one, correct? But I need to say that it's not totally correct. They based on some of the background information. But if all the system is the same, we can think about what the variations means. When variations very large, that means they are easy to release the waters and store the waters. Something like that. Or we mentioned that the storage coefficient is the unique head decline, how much water release, right? If we're using this concept, water release, for example, like that. So if we assume the water release amount is the same, so that means your S and your head is the inverse proportion. Your S value and your head variation will be inverse proportional. That means you have high variations, you should have small S values. And if you have the small variation, that means you have high S values. But as I mentioned, we assume this one is the same. But honest for the in situ is not, because we don't know how much water they release or obtain. They might depend on your pumping behaviors. But if we assume they are the same, they should have this kind of correlations. So that means commonly have the high variations means your S value is very small. So that means you have the very small disturbances of the waters. You will have high variation for the head. And this one means even you take a lot of waters, but the S value, they can provide or they can supply a lot of waters. So even you pump a lot, they're still very stable. So that means they can provide more waters. Storage, something like they can provide more waters, right? So that means if you pump in the same quantities, this one will be relatively stable, and this one will have larger variations. Okay? And another could be this kind of behavior. If you know the in situ conditions, 高速 is around the proximal fan area, top fan, proximal fan area, and to cool is in the middle fan areas. So this one is a gravel, commonly for the gravels. So gravel will easy to have the water store and water release. So commonly their variation is large. But for the if you have the very good aquifer system, like you have the coarse sands or fine sands, and very thick waters, they can supply a lot of waters, and then your water variation will be relatively stable. Relative, but not exactly, because they have some other background information inferences. Yeah, so this one is to let you understand the concept. Not always correct, but the concept. Commonly, small variations means they have higher capacity, and larger variations means they are easy to have the disturbances. Easy release, easy store. And which one is a good aquifer to provide waters? Which one is better? if you are the groundwater hydrologist and government asks you, you have two sites, you should you want to gather waters, which site you should select, this one or this one? How to make a decision? Which one is better? Upper one? So that still depends. For example, gravels, they do not induce much subsidence problems because they are relatively rigid, or the grain size contact very solid, so they are not easy to have the deformations. And this part is also very easy to have the recharge and discharge. Okay, so if we take a look the overall, this system could be good aquifer system because they can easily have the store and take waters out. But another way is if we take a look at the storage, they also imply that the water might not be sufficient because they are easy to decline very largely. Or they might imply that you need to put your pump to be relatively deep. For example, if they have the variation like they have the around 50 meters, okay, their water level can decline to the 50 meters. That means your pump need to put deeper. Maybe you need to put here or put here your pump. And you can see that if you put it in 40 meters, the upper part could be 75 meters. They can have the 35 meters variations. And pump might not have some problems because I don't know if you understand that the device, they have the limitation for the water depth. Device commonly have the limitation to the water depth. Some of the device, you put it too deep, they will broken because the pressure is too large. They will have the waters infiltrate to your device, you will broken. So they have limitation to put in the waters. So if your pump have these problems, you cannot put too deep. So you will get the problem because if you put the pump here, that means in the dry season, your pump will export. So you will only pump the airs, you cannot pump waters, and your pump will broken. Okay, so that means you need to be deeper. But when you put deeper, that means in the wet seasons, your pump will be very high pressures in the deeper part, and sometimes it might broken. And for this one, although they might be easy to induce some problem, but we don't know exactly what's the exact meaning. For example, if they have the clay materials, maybe they are not easy to pump waters out and store water in. So they will still relatively stable. And they might imply you cannot pump a lot of waters. Okay, so we cannot just use that to decide which one is better. We still need to do the pumping test in situ to quantify how much water we can pump. Okay, so some researchers in Taiwan, I see that they're using the variations to quantify is the area suitable for water exploitation or not. It's not correct. It's not correct. Yeah, so be careful for this. If you have this sense, this one they represent, maybe they have high S values, but high S value may not exactly have the suitable for the pumping. Okay, and this one they have higher variations, maybe not suitable for the pumping because they have small S values, but they might represent the high porosity conditions. They can store more waters inside. So that still depends, not exactly you can use in this quantity to understand is the aquifer suitable or not. Okay. Yeah, but that's just an example. Not as I mentioned, we need to confirm if the volume is the same or not. So very quickly summarize. Natural geological material contain voids or space. The porosity is the is a measurement of the volume of the void of the total volumes to a sample. Permeability is a measure of the ability of the material to transmit fluid. And hydraulic conductivity is the important physical property of the groundwater flow in a microscope point of view. Darcy's equation is one of the most important equations used in the groundwater flow, but it has some limitations. We mentioned that turbulence flow cannot be used or nonlinear flow cannot be used. And there are two main aquifer parameters of importance. We call the transmissivity and storativity. So in the in situ pumping test, we commonly estimate is the T value and S values. So in the following, maybe in the last half semester, we're talking about the hydraulic test or the pumping test. We will teaching you how to estimate the T and S values for this. Okay, so this is very important for the groundwater hydrology. And the basic concept is like this. We have porosity, we have hydraulic conductivity, we have the Darcy equations. But honestly speaking, porosity is not very commonly used in the groundwater flow system because we use in microscope point of view. We only consider flow in and flow out. We don't care about the detail inside. So in the equation, we do not use in porosity. But for the contaminant transport, porosity will be important because we need to understand the solid phases influences the free channels. Okay, so this will be different concept. Any question about this part? No? Commonly do not have any questions, right? Okay, if no question, we'll continue our lectures. The following, we're talking about the theory of groundwater flow. And you will see that the groundwater flow equations borrow from the other physical equations because we don't know exactly the behaviors for the groundwater. So in the past, Henry Darcy, he tried to using the concept from the others. So the first, what drives the groundwater flow? We already know that is the hydraulic head. So the hydraulic head, we borrow from the Bernoulli equations, the energy concept. So originally, the head have three terms we mentioned previously: elevations, pressure, and velocity. But the velocity is very small in groundwater flow system. We ignore this. So we only have the pressure head and elevation head. And it seems the whole equations needed to have the same unit. So we divide by gamma W, and this divide by 2G, and we can get that all the unit will be meter, 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 meters. Okay, so there's a physical equations we need to follow in this. So hydraulic head, or we call the total head, is the elevation head plus the pressure head. We already know that. And we're using the Darcy experiment to do the calculations or to understand the behaviors. So Henry Darcy, he tried to using this system and using the experiment result to estimate the Darcy's law. So for the description for the groundwater flow is based on two equations. One is Darcy's law and the other is continuity equations. Darcy's law is to describing how fast the water flowed, and continuity equations is to describing the water mass conservations. So when you see continuity equations, they're equal to the mass conservations. So you can have this kind of concept. It describing the conservation of the fluid mass during flow through a porous medium, result in partial differential equation of flow. So we know that the mass will not disappear under the normal even a reaction, chemical reactions. So we call that the continuity equations. That means if we have the interface, the flow in need to equal to the flow out. Okay, so there's the continuities. But if we have the volumes, we have the flow in and flow out. We also have some waters maybe stuck inside, or they take time to flow through that. So we have we call the storage. We were talking about this. And Laplace equation is the most important in math because we were using Laplace equations to combine them together. And for the groundwater flow theories, we're using the elementary volumes. We call it IEV, we mentioned previously. So that means in these IEV systems, we assume they are homogeneous. Okay, so in this cubic, the property is the same. They look like the element that we do in the simulation in groundwater flow model. Okay, although there could be difference, but it look like. So in the elements, we still using that kind of concept. So that we are flowing for out and storage. So all of the equations derived from this. The differential equation for the quantum flow are developed from principle of mass conservation in a representative elementary volume, REV. In words, such a conservation statement can be written by mass flow in minus mass flow out equal to the change of the mass storage with time. So if there's interface, it will be easy to imagine the flow in need to equal to the flow out, as I mentioned. But if we have the space, the flow in and flow out, sometimes they have the time lag. If the system is quite large, flow in, flow out, it takes time to flow to that area. So they might have a kind of time lag. Okay, that could be, we call it storage. Or that could be, if we connect to the storage concept we mentioned, they can expand the matrix, or they can compress the waters inside. They still able to have the storage concept. Okay, so they will not equal to, not the flow in equal to the flow out. They will have some residuals be stuck in the elements. So we call it storage concept. REV is defined as volumes exhibit the average properties of the porous media around a point called PSYZ, which in the center of the volumes. So we put it here PSYZ, and we use in the cubic, and we assume that there's dx, dy, and dz. So that dx, dy, dz represent these elements. Okay, so that means in the centers we have after the half x values, we have the x plus ds divided by 2 for this surface, right? Because this is centers x, and this is dx. So that means the centers, we have the half dx. So this is this surface, and minus dx is this surface. And y and z have the same, but if we're using x directions to represent that. So that means water flow in to this matrix from this surface, and then flow out, the water flow out from this surface, right? We need to have the cross-section because we need to calculate the volume. Assume that the water mass flows through the 6 phases this is mass, so m from S1, S2 means one is in, one is out. And furthermore, rho is the free density, and n is the porosity of the REV. Above equation can be written in the mathematical terms. We using the mass, flow in minus flow out. Okay, flow in minus flow out, flow in minus flow out. There will be the storage, the differences will be the storage. We're using the volumes, ds, dy, dz is the elementary volumes, right? The total volumes. And we multiply porosity, they become the water volumes. Remember that I mentioned? Volume multiply porosity become the water volumes. And water volumes multiply density become the mass, right? And mass change with time. So this one, we call this the mass change with time, or this the same. This is the flow in, flow out, but this is the max flux. So they also means the mass divided by time. So this is mass divided by time, this is mass divided by time. So these physical equations we can write down like this. And this term we call the storage term. And flow in minus flow out, flow in minus flow out from 3 directions. So it means we have 6 surfaces. So we have 6 flow directions, right? And if we assume they are just one direction, so we can cut these equations. The mass flux of the waters in direction I is expressed as like this. So we can have the mass in S directions or in Y direction. All of that could be okay. And there will be the Q is the velocity, Darcy velocity, and multiply cross sections. So velocity multiply cross sections become the volumes. Volume divided by time, right? If we have 1 meter per second, that means 1 second they can have 1 meter's length. And we multiply cross sections. That means 1 second they can have this volume of the waters flow through the system, flow the cross sections. And this is the volumes. Volume multiply density. So this one become the volume flux, the mass flux. Q is the I component of the Darcy velocity, and delta SI is the area perpendicular to the flow directions I. So as I mentioned, this is the velocity multiplied cross sections. So this is the volume flux multiplied density become the mass flux. So this mass flux is to represent each of the mass flux like that. Okay. And to obtain the mass inflow and outflow rate in the x directions of the IV, we derived the expressions low QS across each of the surface. Taylor expansion series at the outflow surface is given by Thomas. So that means in the previous equations, this one, we combine these two together, dou and Q together, and using the Taylor expansions. And we have the, one surface is the, the central point on the right hand side, and minus, that means the central point on the left hand side. Do you remember that? We have this surface and this surface. And this one is x, and this one is the x plus ds divided by 2. So this is another surface. So we're using the flow across this surface and the flow across this surface. Okay? And this one plus means the right-hand side surface. Okay? So we expand this equation, this term to be the Taylor series. So we can write down like this. Detail you don't need to memorize, just remember the concept. So they become like that. And another term on the left-hand side surface, we can have another surface for this. And we can see that they have the plus, negative, the plus, plus. So if we using the mx1 minus mx2, and then it means the same unit, the same term, this term will be eliminated. Right? And this term will be eliminated and only have this term left. Because this divide by this one, not divide, this one minus this one, become this one plus this one. Okay? So if we eliminate the high order term, they become like this and this. And then ms1 minus ms2. So they become like this. This is the same, this is the same. And this is, we expand for the Taylor series, but we multiply the cross sections. The cross section will be the same, dy, dz. This is ds, this is dy, this is dy, this is dz. So this cross section is dy, dz, right? Cross sections. This one, we expand this one, and this one will be dy, dz, and this one can use in the Taylor series. So after that, we only have this term. And we have ds, so put it ds out. And so this term like that. So that means mx1 minus ms2, we got this term. Is that okay? So in the x directions, we have the mass flow in minus mass flow out. And this is a flow, mass flow result. So we can multiply y and z together. So we got together like this, right? And this is a minus because we're using, remember that when we derive equations, you need to be careful for the sign. Sometimes they are negative, sometimes they are positive, depends on the equations. Is that okay? Like this? So the change in water storage within the IV, this is another term. The change of water storage is, we write down like this. I don't know if you remember, go back. This one. Okay. In the previous, we try to derive this part. And then we go to this part. So this part right now be simplified to this one. They combine together, become like this. And this is the right-hand side term, okay? So right-hand side term, how to combine them together? Okay, right now they just put it together directly. So this is the left-hand side. This is the right-hand side, right? In the previous equations. And we can see that ds, dy, dz, so they are the same, so we can eliminate. So after that, we have this term equal to this term. Is that okay? Which one? The previous part, we used in Taylor expansions. We got a term, and this one is the right-hand side, right? So left-hand side equal to right-hand side. Right-hand side is here, the same. So the previous one, we derived the left-hand side result. So this is the left-hand side result. And this is the right-hand side result. We do not change that. And we can compare to the left-hand side equal to the right-hand side. So this is the same. We eliminate. So we got this part equal to this part. So become like this. Okay? Can you follow? Okay, so by making the further assumptions that the density of the fluid do not vary spatially, and the density term on the left-hand side can be taken out as a constant so that the equation becomes like this. So if the density do not have the spatial differences, all of the locations, the water is the same densities, so we can take the density out. So take density out, and we divide to the right part, become like this. So this term only have the partial QS, partial S, partial QY, partial like this. And the right-hand side like this, okay? And the right side above equation is related to the specific storage of an aquifer. So the detail is ignored, okay? This term, we're describing how the waters release or the store in the systems. So it can be simplified related to the hydraulic head. The detail you don't need to memorize, but as I mentioned that this part we use in the water expansions and matrix compressions. So originally, you have the deformations inside. But right now, we simplify them to be one parameters, SS. Okay, so the SS, remember that it represents the deformation. It represents the realities for the deformation, but right now we assume it is just a constant, it's the quantities there. So we can change this term to be the storage term like this, and change the partial differential equations to be the head, H values. So SS is specific storage, and H is the hydraulic head. So right hand side we shifted to this. So right now it's this equal to this, right? And Q is the Darcy's law. Q is Darcy's law. QS, QY, QZ, we mentioned that. So Q equal to minus KIA, right? So you can put minus KIA inside here. Minus KI, not KIA, because we only have the Darcy's velocities. Okay, so using partial H, partial X, but we have three directions, KX, KY, KZ. So we put them inside, so they become like this. And originally they have the negative, and this is negative, so negative term eliminate. Okay, so we got the left-hand side like this. The right-hand side is this term. We press the storage term. So to here, okay? Can you follow? Or maybe you can go back to take a look at the slides by yourself. Maybe you can repeat or try to derive by yourself. So the above equation is the equation of ground flow in a saturated media under transient state situations, and also for the confined aquifers. They can be written in many forms and applied to variety of the different conditions. Okay. So this term, this equation is a general equation, although it's not so general, but it's commonly seen like that. For more general, you might see the K value be taken out. K take out, you will have the K partial H, partial square H, partial S square, and this is the same and the same. And when you can take K out, When you take K out, means your K do not vary with spatial domain. If your K take out, means your K do not is independent. If your K depend on your partial your X, this one you cannot be take out because they will change in the spatial domain. So you need to keep that. So for the homogeneous system or for analytical solutions, when you take this out, that means you assume the homogeneous. But when you're doing the numerical modeling, you cannot take out because your K in different grid will be different. So you need to keep the format like this. And what's the Kx, Ky, Kz here? Remember that K represent directions. So this K represent the flux in X directions, in Y direction and in Z directions. So this K, X means isotropic or an isotropic concept. You have Kx, Ky, Kz means at the data elements, your K in the X, Y, Z direction is different. So you're using X, Y, Z. If they are the same, you are using K, K, and K. They are just one K. Or you can using KH, KH, and KV. Commonly, we'll assume X and Y have the same quantities, and Z will have small quantities. So you can use in H and V, vertical and horizontal. Okay, so S, Y, Z means directions. And this outside, X, Y, Z means the spatial domain. So that means in this system, you can have the different locations, different directions. In the later, we'll have more detail for this approach. Maybe you will take a look one more. Okay. So another, we can consider the sink and source. Sink and source is the kind of we put the waters in data elements. We use in IEV to derive equations. So sink and source means we put additional water in or take the waters out directly, like we inject waters or we pump waters from data elements. So this kind of a term we call it sink and source or source and sink. Okay, and we put it directly in the equations. But another is boundary conditions. Boundary means you float from the boundaries into the system. But that's not in data elements, so the concept is different. Although they represent a similar behavior, but the concept is totally different, okay? And the setting will be also different. So in the following, we're talking about what's the unit here. You need to pay attention for the unit. Because you might think about source and sink. I just put the waters in and take the water out, so they should be the volumes, or have the volume and time. But no, okay. Yeah, next week we'll take, not next week. Next 2 weeks, we'll take a look what's the unit. Okay, so be careful for the unit. Again, I try to emphasize that. When you try to using the equations, or when you try to do the quantification for your modelings, be careful for the unit. That's a very important part. Okay, seems the time. I don't know if you have any questions about the content. Okay, if no, we'll stop here. And since next week we will not have a class, we suspend the class. I go to a conference, and after that we will have the midterm exam. And midterm exam, I will put the information on the E-class, the question on the E-class. You need to download and write the questions before submit before the end of Friday. And that week we also make up a class. So in the October 30th, remember to attend, to show up here, okay? We have the exam that week, but take home. But we have a class in physics here, okay? And after that, we'll have some arrangement. You missing that we will have the field trip in November 20th. Yeah, so that's that day. I don't know, that's the holiday. For not a holiday, the sports day for NCU, so we will not have a class. Yeah, so let me know if you have any questions, and remember to prepare your A4 report as soon as possible. Because after the midterm, we will have very quick to have the presentations. I forgot one thing. We have not separated the group, right? The group 1, we need to present in the first week. So who want to present in the first week? Any volunteer? What? We have 8 students, so we need to have 4 students present in the first week and 4 in the second week. So we want to be the volunteer for the first week. For which team? We have 4 teams, and 2 teams need to present in the first week. Any volunteer? Okay, good. And how about the others? Or you want to have the compete to see who will present in the first and second? First week? Okay, thank you very much. Yeah, so we have 2 groups present in the first week and 2 groups in the second week. And we have schedule, I'll upload to the e-class, you can take a look. Okay, yeah, like that. Thank you very much.